In this video, we're going to take a look at how to find the pH and the percent ionization for a weak acid, a weak monoprotic acid. The question is actually question 30 in your homework booklet. I've added just one piece to the problem, the percent ionization. So the first thing we're going to do is realize that we're dealing with an acid, and so we're going to write a balanced equation for an acid reacting with water. As we write the equation, keep in mind the Bronsted-Lowry definitions of acid and base. So the acid here is benzoic acid, and it's got this long formula, C6H5COOH. It reacts with water. Now, the definition of an acid, according to Bronsted-Lowry, was a hydrogen ion donor. So the hydrogen ion at the end of benzoic acid, the hydrogen bonded to oxygen, is going to be donated to the water molecule. That means the water molecule is behaving as a Bronsted-Lowry base because it's accepting a hydrogen ion from benzoic acid. When water accepts the hydrogen ion, it'll become the hydronium ion, H3O positive. Keep in mind that the hydrogen is positive. So when a neutral water molecule accepts a positive ion, the hydronium ion will then have a positive charge. The benzoic acid gave away the hydrogen, so its conjugate base, the thing that's left after it donates hydrogen, will be C6H5COO minus. Minus for a couple of reasons. One, because it lost a positive, so it used to be neutral at the beginning, it lost a positive, so now it'll be negative. Another way to look at it is that everything on the left was neutral, but on the right we had a positive. So we have to make the charges the same on both sides of the equation. So if there's a positive here, there has to be a negative here, so that both sides will be zero in this case. Now, the water is liquid. If you want to put the phases in, it's a liquid. Everything else is in the water, so everything else is aqueous. Because water is a liquid, we're going to put a big X under it in our ice table that we're going to create. It's not going to be part of our equilibrium expression. The acid, the benzoic acid, was 0.042 molarity initially. Now, how much hydronium is initially in water? We know that at 25 degrees Celsius, the pH of pure water is 7. So that means that there has to be some hydronium in water since pH is based on hydronium. Since the pH is 7, it means there's 1 times 10 to the minus 7 molarity hydronium in pure water. And we know that that comes from the self-ionization of water. That amount, though, is so small compared to what this acid is about to produce that we will ignore it and say that there's essentially no hydronium in the water initially. There certainly isn't any benzoate ion, the conjugate base, initially. Now, before we go any further in the ice table, consider whether or not the acid is weak or strong. The Ka value was small, it was 10 to the minus 5. If this were a strong acid, the Ka would simply say large. It would be a number bigger than 1. If the Ka is smaller than 1, like this, then you're dealing with a weak acid. So let's just go to the side of this table. I'm going to squeeze that in. This is a weak acid. And the reason I want to think about that is because that tells me that it is not 100% ionized. A strong acid dissociates or ionizes completely. If this were strong, we would lose 0.042. But because it's weak, it does not ionize completely, and to complicate things, we don't know how much ionizes. So we'll say that it ionizes, it loses X. Now, the ratio in the equation is 1 to 1 to 1. The coefficients here are all 1s. So if the acid lost X, there must be gain X for hydronium, and you gain X for benzoate. So that means at equilibrium there will be 0.042 take away X, the concentration of the benzoic acid that did not dissociate. And then you'll have X, the concentration of hydronium, and X, the concentration of benzoate, the conjugate base. If we write the Ka expression, we can get an equation in which to put these x's. So the Ka is equal to concentration of hydronium, product concentration, C6H5COO minus, benzoate, divided by the concentration of the reactants. In this case, the benzoic acid, the water, being a liquid, is not included. And of course, we're raising each concentration to the power of the coefficient in the balanced equation. In an acid-base reaction like this with water, the coefficients are always 1s. So now, looking at the Ka value, we get 6.5 times 10 to the minus 5, and now substituting our algebra, x times x, the two concentrations in the numerator, will give me x squared over 0.042 take away x, the concentration of the benzoic acid at equilibrium. So now we've got this equation on the right here that we have to solve. If you have a graphing calculator, a TI-83, a TI-84, or something like that, you can use the solver. So I'm going to quickly use the solver on my graphing calculator to solve this, and then I'll show you how to do it without the graphing calculator. So I've got my calculator here, and I'm going to go to the math button on the calculator. So the math button right here underneath the alpha, math, press that. And then if you scroll down, you'll see that there's an option that says solver. For my calculator, it's beside the number 0, so I just have to press a 0 on the keypad down below, 0, and that selects the solver. Now I've used the solver before, so there's already an equation that's been entered and solved. If I press the up arrow on the keypad and then clear, I can delete the equation that was there. So now this is what you'd see on a calculator where you're using the solver for the first time. Now you notice that it says that it wants you to type in the equation, but it has to be in the form 0 equals. Our equation has 6.5 times 10 to the minus 5 equals. To make it say 0 equals, we'll just subtract the Ka value from both sides. What we'll be left with is 0 equals x squared over 0.042 take away x, and then minus the Ka value, 6.5 times 10 to the minus 5. So this equation that says 0 equals is what I'm going to type on the calculator. Now there's a binomial, two terms in the denominator, so I'm going to put brackets around that, especially when I type it on the calculator. So here we go. The X button is right beside the alpha button. It says X, T, theta, N. So press that. X squared. I have a squared button right here. Divided by, open a bracket, 0.042, take away X, close your bracket, and then don't forget now to subtract the Ka value, 6.5. Now we have a scientific notation button, which is the EE symbol right above the comma. So second function EE, which means times 10 to the power of, and then negative 5. So 6.5 times 10 to the minus 5. Now just double check quickly that you typed the equation in correctly, you didn't mistype something, and now press enter. And the way the calculator works when it solves an equation is it requires that you, at this point, give it a guess. You have to type in a number that you think is going to be close to the answer you want. Now, in this question, the chemistry problem, our answers have to be positive numbers, since these are concentrations, but they're usually very, very, very small concentrations. So 99.99% of the time, a guess that will work in a chemistry question like this will be 0. We're saying that our answer is probably close to 0. So now we want to solve the equation, so we're going to press the alpha button, and then above the enter it says solve, so alpha solve, and there's the solution to the equation, 0.0016. Right, so coming back to my paper, I'd say on my calculator from the TI-84 solver, my answer is x equals 0.0016 molarity. Okay? Now we can answer the question. We wanted to know the pH and the percent ionization. Notice that this X in our ice table represents several things. One thing that it represents is the concentration of hydronium. X at equilibrium is the hydronium concentration. That's important because the definition of pH is the negative logarithm of the concentration of hydronium. So write that down, and now type in write down negative log of, and let's put in this concentration of hydronium, 0.0016 molarity. Grabbing a calculator now. I'll get out of the solver by pressing second function and quit right above the mode button. So second function quit takes me back to my main screen. And now I want to take the negative logarithm, log, of 0.0016 and press enter. It tells me the pH is 2.795. I'll round that off to 2 significant digits, which in a pH means 2 decimal places. The number in front of the decimal in a pH is never considered significant. So if I have 2 significant digits in the concentration, 0.0016, I want to keep 2 decimal places now in my pH. So 2.795 will become 2.80. So there's the pH of the solution. The percent ionization is also relatively easy to find, but try to understand how this works, and then you don't have to memorize as much. The percent ionization, you want to find out how much ionized. Looking back at our table, the acid is what's ionizing, and the X is what ionized from the acid. We started with 0.042 molarity, and we ionized, we lost X, the concentration we calculated to be 0.0016. So if you began with 0.042 and you ionized 0.0016, we can calculate the percent ionization by simply taking the amount that ionized, 0.0016, and dividing by the starting concentration, so 0.042, and I'm running out of room here, but times that by 100, and you'll have a percentage. So 0.0016 divided by the initial concentration, 0.042, and then times 100. So 0.0016 on my calculator, divide by 0.042, times by 100, and I get that the percent ionization is 3.8%. So if this were a strong acid, 100% of the acid would have ionized. Because it's weak, we got much smaller percent ionization, only 3.8%. Now we solved that using the graphing calculator's solver feature. If you don't have a graphing calculator, or if you're going to go to the university here and where they don't allow you to use graphing calculators on your exam, you're going to have to use a different approach to solve this equation over here. So let's set it up again and see if we can solve it in a different way. So our equation was 6.5 times 10 to the minus 5 equals x squared over 0.042 take away x. How do we solve this if we don't have a graphing calculator? Well, one method, which we really want to avoid if we can, because it's kind of tedious and it's a little difficult and it's easy to make lots of mistakes in it, we can multiply this Ka value out front by the denominator, 0.042 take away x, and say that that has to equal the x squared on top. In the same way that 2 equals 6 divided by 3 allows you to take 2 and multiply by 3 and get 6 as an answer, we could do the same thing here. Now if you imagine doing that, you'll realize that what you'll get will be an equation eventually that says x squared with some x's and a constant number equals 0. And that sounds like a quadratic equation. And then we could use what's called the quadratic formula to solve it. But it's kind of tedious, and if we can avoid it, we like to do that. So what we're going to use is the method called successive approximations. And I expect everybody in my chemistry class to know how to use this method to solve quadratic equations in a slightly simpler way. The key is to recognize that the Ka value is small. Because it's small, we know that the acid is not really going to ionize very much. In other words, this X here is probably going to be a very small number compared to what we started with. We're not going to be losing very much of the acid here. So what we'll do is we'll state an assumption, and you have to put this in your answer. So we'll say that since the Ka is small, we're going to make an assumption. We're going to assume that X, this thing that we're ionizing, is much less than, so two less than symbols, much less than the initial concentration, which was 0.042 molarity. Now, why would we want to make that assumption? Why would we want to assume this? Well, if X is much less than 0.042, therefore 0.042 take away X, the thing that we have on our denominator in the equation, is going to be approximately equal to 0.042. In the same way that if you had $1 million and you lost 10 cents, something very, very small, you'd probably still claim that you're a millionaire, even though you lost 10 cents. You'd still say you have $1 million, because that 10 cents doesn't really matter. So since X is going to be very, very small compared to 0.042, our acid is very weak, we can basically ignore this X on the bottom here. That'll give us a new equation. 6.5 times 10 to the minus 5 is approximately equal to X squared over 0.042 instead of 0.042 take away X. This equation is actually much easier to solve because there's no X in the denominator. We can grab a calculator and very quickly solve it. But the solution is actually not the solution to the original equation. It's the solution to the simpler equation. So what we're going to call this is our first approximation of what the answer was to the original equation. So x1 equals, now we're going to solve this the same way we would do this over here. 2 times 3 equals 6. So the Ka times 0.042 equals x squared. So on my calculator, I want to type in 6.5 times 10 to the minus 5, multiply that by 0.042, and press equals. This is equal to x squared. To get x, I'm going to square root that number. So I have a square root symbol right above the x squared button on the calculator, so second function square root of that answer. Now you could type it in, or right above the minus symbol at the bottom of the calculator it says answer, ANS, so we can take the square root of the answer and then press enter. x1, my first approximation of the solution, is 0.0017. I got 0.00165. I'll round that off to 0.0017. Now that's my first approximation. To get a second, and this will be a better approximation than the first, we're going to take this first answer and we're going to place it back into the original equation, and here's the key. We're going to place it back where we ignored the x, which was in the denominator. We had the equation down here, just 0.042, so we ignored this x in the denominator here. So on my calculator, let's take 0.042 and subtract our x value that we got as our first approximation, 0.0017 equals. This is my new denominator in the simpler equation. So we're going to take, instead of 0.042, we have 0.0403. So let's solve again by multiplying this by the Ka value, and then again square rooting the answer. So multiply that by Ka equals, and then square root the answer. We get a second approximation, 0.0016 molarity. So just one more time, we took the first answer, we put it into the denominator in the original equation because we had ignored this x. That left us with an equation that said 6.5 times 10 to the minus 5 equals x squared over 0.042, take away 0.0017. We solved that equation in the same way we did this one, by multiplying the denominator by Ka and then square rooting. We got a second approximation. Now notice our second approximation is very similar to the first. In fact, I would be tempted at this point to just stop approximating because the answer is so close. It changed by 1 in the last decimal, 0016 instead of 17. But if we want to go one more time, we can get a third approximation. We'll take this 0016 and we'll put it back in the denominator where we had ignored x. So let's do that. So I'm going to clear this. 0.042, take away my second approximation, 0016, equals, this is my new denominator. Multiply that by the Ka value, equals, and now square root the answer, and I get a third approximation that is exactly the same when I round it off to 2 significant digits as my second approximation. So I'm going to stop there. The method is stopped, we stop doing that cycling through when our approximations become equal, in this case 0016. Now if we compare that to the answer we had using the solver, you'll notice it's the same. With the solver we had 0.0016 also. So once you've got your x value here, you would now do what we did previously. You'd go find the pH, and then you'd find the percent ionization. Now this was a little bit of tedious work, I agree, but it's still a lot faster and a lot easier than using the quadratic equation. And if you don't have a graphing calculator, or if you're going to use go to university and study chemistry where they don't allow graphing calculators, this is the way you would solve that quadratic equation without the solver feature on a calculator. So there we have it, a weak acid pH problem and percent ionization solved first with a graphing calculator and then using the method of successive approximations.